Hey everyone, what I want to do for you now is go through a review of everything we've done in Unit 3. There was a lot of information, so I wanted to make sure that you are all on the same page as we went through there. So, as we've seen, we saw that light was a particle in Unit 2. In Unit 3, we're trying to prove that light is a wave. So the first thing we came up with was how light intensity changes. We said that as the light spreads out in all directions, the intensity, how strong the light interacts with your eye, dies off by this 1 over distance squared idea, or this inverse square law. We came up with the butter gun idea that if you move it twice as far away, the butter can spread out in left and right directions and up and down directions. If you spread out even further, it can spread out 3 times more, up and down and left and right. So the intensity of light drops off by 1/4, by 1/9, by whatever distance you pick squared. But it can also do the reverse. If you move closer to the object, the intensity can increase by 1 over distance squared. So make sure you know how to go through scenarios like this. And we did practice problems in class talking about the intensity of light at Pluto versus here, or we did on the quiz where we said the light drops off by a factor of 6. How far away did you move? So let's try that example. So if the intensity of light is subject to this 1 over d squared, this inverse square law, and I say that the intensity is dropping off by a factor of 6, what I need to do is divide this side by 6 and solve for what distance that equates to. So if I'm doing 1/6 equals 1 over d squared, I need to set that equal and solve for d. So really I get d squared equals 6, and if I want to solve for the distance, it's the square root of 6. You can do that in a calculator and tell you exactly how far away you'd have to get to drop your light intensity by a factor of 6. If I wanted to increase my light intensity by a factor of 6, that would be multiplying this intensity by 6, which means that your formula would change just slightly and you'd be left with 6 equals 1 over d squared, which means that d squared now would equal 1/6, and you'd have to square root both sides to figure out what distance you'd have to get to make your intensity go up. You'd have to get closer to the object, but how much closer we can do with our math. And we also talked about that and equating that to solar panels, that when you are trying to gather light from the sun, the further you get from the sun, since we know light spreads out, the bigger the panels have to be to collect the same amount of light they did on Earth. Or vice versa, if you want closer to the sun, you can actually use smaller panels to get the same amount of energy you would get here on Earth. So then we had our debate about light being a particle or a wave, and if you click the video there, you'll see that it can take you back to that link where we watched light being a wave because of this idea of interference upon itself. So we made the candy wave and talked about what waves are. Talked about things like the crest of a wave, the trough of a wave, the wavelength from any two identical parts of a wave, the amplitude of a wave, remember was the height of the wave, and this frequency and period idea. Frequency being how often a wave occurs, and time period being the time for one wave to pass. So we solved many different problems with this. We said that light is electromagnetic radiation. So there is a large spectrum of light, and we're only able to see this tiny little sliver we call visible light. The white light coming from the sun is made up of every color in the rainbow, and from that we can look at shorter wavelengths being more energetic, like ultraviolet, X-rays, and gamma rays, and longer wavelength light being less energetic, like infrared, microwaves, and radio waves. So we've talked about the spectrum, and that's really why we get the different colors that we get. Red light has bigger waves, and blue light has shorter waves, which is why that quote from Neil Tyson in the beginning says that Rudolph the Red-Nosed Reindeer was the perfect pick. Red light has long waves and can make its way through the fog. The blue light would be scattered very quickly. So then we said if light is a wave, we can use wave speed equations to solve for the speed of waves. And if we're talking about a light wave, just put the speed of light in for your wave speed. Wave speed is equal to wavelength times frequency. Since the speed of light never changes, as we change the frequency of light, we change its wavelength. And that's how we see different colors or forms of light. We talked about polarization too. Make sure you understand the polarization and what the polarization was doing. It's really just a fence. As the light is vibrating in all directions, only light that shakes in the direction of the filter can make it through. So if the two filters are parallel to each other, then the light passes through the whole way. But if you turn them 90 degrees, that's when you can block light completely. If light was just particles, it would pass through those fences no problem. But since it is a wave, it is getting absorbed if it doesn't make it through those fences. We then went in the planetarium and we talked about every color under the rainbow, and we mixed colors like red and blue, or red and green, or blue and green. Hey, we even mixed all of those colors, and when we mixed all those colors, we get white. So remembering that the colors go from red all the way to violet, if you turn on the red, the green, and the blue, you cover pretty much the entire electromagnetic or visible spectrum, which our eye interprets as white. So mixing those colors, remember how we got yellow, cyan, and magenta, and how you can get any other kind of mixes in between there. Another proof that light is a wave, besides the picket fence, besides the different wavelengths giving us light, was this big idea of interference. And that's what the video was stressing, that light was interfering with itself. Before the interference, the waves could be in phase with each other, crest with crests, or trough with troughs, or they could be out of phase with each other, a crest on one side and a trough on the other side. And we looked at how waves interact, so we wanted to describe that motion, or what happens when the waves actually hit each other. And like it says here in the note, the amplitudes will either add or subtract when the light interferes. So that it can add constructively or destructively to either build the wave up or destroy the wave and try to bring it down. So bright light and dots were constructive interference, where destructive interference is when the light dims or you get no light whatsoever. It's light canceling itself out. So looking at an example here, here's some from those packets of the snapshots of waves, and you can watch as the waves move towards each other. Since they are out of phase with each other, they completely cancel each other as they move along. And especially right here in the middle here, both the top and the bottom part of the wave are on top of each other, so the wave perfectly cancels out. In the next frame, you can see that part of the purple wave is mixing with part of the orange wave and canceling out the heights of both. But once the waves interfere, they just pass on and keep on moving like nothing ever happened. So it's not that waves hit and bounce off each other, they actually pass through each other and their amplitudes combine. Here's another one from your snapshots of waves. Watch these two waves meet. So in this one, we've got everything going on. We've got construction and destruction. As the waves meet, they start to destroy each other as the orange overlaps with the purple. In the next frame, you can see that right there, the crest and the trough of the orange and purple wave overlap, and you get that flat wave in the middle. However, the other two parts of the wave haven't even touched each other yet, so they don't think anything's going on at all. In the next one, you can see lots of cancellations happening here. You're getting cancellation right down the middle, but actually where the two peaks of the orange and purple are meeting, top and the bottom, you can see that's filling in and flattening out the top of the wave. In the next one, the crests are meeting with the crests and the troughs are meeting with the troughs, which are giving us very, very large amplitudes and peaks. And then right after that, they move on like nothing ever happened. So that's what we mean by interference. Go to the PhET simulator, go to waves on a string, and play around with that and watch how waves interfere when they meet up with each other. And the last thing we talked about in here was how we can measure distances to stars. And so it doesn't really prove that light's a wave or a particle. Light, whether it's a wave or particle, follows this parallax idea. But when you try to measure things from two different positions, that object will shift if it's close, and it won't really shift if it's really, really far away. So we can use our trig, and we practiced using our trigonometry in class, and we know that stellar parallax happens for stars when we view them at different positions around the sun. So we know that we are moving and not the sun moving because we see stars shifting when we look at them in June versus when we see them in December. 6 months apart is how we can measure our stellar parallax. And it's a very, very tiny angle, and you can still use the same trig we used in the classroom. But the nice thing is, once we do this, we get distances that are much further away. The angles are extremely small since the stars are very, very far apart from us. with small parallax angles, we can use that relationship we used on the worksheet. So we have this equation on the worksheet that the distance to a star is 1 over the parallax angle. That's what P means. If you want to measure your parallax angle, make sure that your angle is in arc seconds. And when you get your distance, 1 over arc seconds will spit out your distance to the star in a unit called a parsec. So if you want to know how far away something is in parsecs, get the parallax angle and do 1 divided by that parallax angle. If you get parsecs and you actually want to put it into light years, then you can stretch it out and convert one more time. Those are the topics that we talked about in class. You will have your equation sheet for the test. No need to memorize any of the formulas, just know how to use them and do them. So good luck. See you tomorrow.